Good morning, everyone. Welcome to today's lecture regarding a vital topic in thermodynamics, that is stored energy, transient energy, and total energy. Understanding the different classification of energy is absolutely essential for any serious analysis of thermodynamic systems. Without a clear grasp of this concept, it's difficult to accurately model the behavior of engines, power plants, refrigeration units, and countless other engineering applications. Energy, as we have already discussed, is the fundamental capacity to do work or to transfer heat. But not all energy is created equal. It exists in different forms and it interacts with systems in different ways. Some energy is contained within the system, some is in the transit, and some represents the overall energy content. Knowing how to categorize energy correctly allows us to build more accurate thermodynamic models. In this lecture, we will systematically address these critical distinctions. Our agenda includes defining the stored energy. We will begin by defining what constitutes stored energy within a system. We will explore the characteristics of stored energy and provide examples of how it manifests itself. Next, we will see the concept of transient energy. We will unravel the concept and significance of transient energy. Transient energy refers to energy that is in transit, crossing the boundary of a system. We will examine how transient energy differs from stored energy and why it is important to account for it. And finally, we will see calculating the total energy. We will focus on the calculating the total energy of a system. This involves understanding how energy is stored and transient energy contribute to the overall energy balance. By end of this lecture, we will possess a clear and comprehensive understanding of how energy is classified in thermodynamics. You will be able to distinguish between stored energy, transient energy, and total energy. And you will appreciate how this classification influences thermodynamic process. So let's embark on this journey into the fascinating world of energy, unlocking its secrets and revealing its essential role in the universe around us.
Let's begin by precisely defining what we mean by stored energy in thermodynamics. This is a crucial concept as it sets the stage for understanding how energy behaves within and around a system. Stored energy refers to the energy that is contained within a system and that is not currently in the process of being transferred across the system boundaries. It resides within the system control volume and is associated with the system state at a specific moment in a time. Think of it as the energy that is locked in or held within the system. Stored energy possesses some key characteristics that distinguish it from the other forms of energy. First one is the thermodynamic property. Stored energy is considered a thermodynamic property. This means that it has a certain value and it depends only on the state of the system defined by its properties like temperature, pressure, and volume. The unique value for each unique state of the system, there will be a corresponding unique value of stored energy. If you change the state of the system, example, by changing its temperature or pressure, the stored energy will change accordingly. And finally, it is a state function. Critically, stored energy is a state function. This means that its value depends only on the current state of the system and is completely independent of how the system reach that state. The path taken to arrive at a particular state does not affect the stored energy. It only depends on the current state. To illustrate this concept, consider a simple example of compressing a spring. If when you compress a spring, you are storing energy within it in form of elastic potential energy. The amount of energy stored in the compressed spring depends only on its compressed state, that is, on how far it has been compressed from its equilibrium position. It doesn't matter whether you compress the spring quickly or slowly, smoothly or hurriedly, the stored energy will be the same as long as the final compressed state is the same. Now that we have a clear definition of stored energy and its key characteristics, now let's explore some of the common types of stored energy that we encounter in thermodynamic systems. As we have seen the definition of stored energy, now let's examine the three main types of stored energy that are commonly encountered in thermodynamic systems. They are internal energy, kinetic energy, and potential energy. So, internal energy, as we have discussed previously, represents the total energy associated with the microscopic component of the system. Okay, microscopic means the energy content of atoms and molecules. It's the sum of all the kinetic and potential energy at the molecular level. This includes the energy of the molecules, random translational motion, their rotational motion, their vibrational motion, and the potential energy arising from the forces between the molecules. For example, consider a hot cup of tea. The molecules inside the tea are constantly vibrating, rotating, and moving around randomly. The sum of all this microscopic energy is the internal energy of the tea. The hotter the tea, the greater is internal energy. Coming on to the kinetic energy. Kinetic energy is the energy possessed by a system due to its motion as a whole. It's the energy associated with the overall movement of the system, as opposed to internal motion of its constituent particles. Kinetic energy depends on the system's mass and its velocity. The relationship is given by the well-known formula. Kinetic energy is equal to 1/2 mv square. For instance, a moving car possesses kinetic energy. Faster the car is moving, the greater its kinetic energy. A stationary car has no kinetic energy. Now next is the potential energy. Potential energy is the energy stored within a system due to its position or configuration. It's the energy that the system has the potential to release or convert into other forms. The most common type of potential energy in thermodynamics is gravitational potential energy. This is the energy an object has due to its height above a reference point. It's calculated using the formula potential energy is equal to mass into gravity into height, where m is the mass, g is the acceleration due to gravity, and h is the height. For example, consider a water which is stored in a dam at a certain height. This water possesses gravitational potential energy. When the water is released and flows downhill, that potential energy is converted into kinetic energy, which can then be used to generate electricity. Now that we have a solid understanding of stored energy and its various forms, let's turn our attention to another important type of energy, that is transient energy. As we will see the transient energy also plays a very crucial role in how system interacts with its surrounding. Now, next important slide is this unveiling this transient energy. What is this transient energy? Let's shift our focus to a different type of energy, that is this transient energy. Understanding the distinction between a stored energy and transient energy is critical for accurately analyzing how energy interacts with system. Unlike stored energy, which resides within a system boundary, transient energy is energy that is in transition between systems. It's energy that is actively crossing the system boundaries, moving from one system to another. It doesn't remain confined to a single system for a significant amount of time. Think of it as energy in motion, energy on the move. Transient energy possesses some key characteristics that set it apart from stored energy. Not transient energy is not a property of a system. It is a crucial distinction. Okay, you all students should know this important point, because transient energy is constantly crossing the system boundary. It cannot be attributed solely to one particular system. It's energy that is being shared between systems. And also, transient energy is path dependent. This means that the amount of transient energy transferred can depend on how energy is transferred. Unlike stored energy, which only depends on the initial and final state, transient energy depends on the process or path taken during the transfer. Transient energy can move from one system to another in different forms. The two primary forms of transient energy are heat and work. Heat is the transfer of energy due to temperature difference, while work is the transfer of energy due to force acting over a distance. To put it simply, if energy is crossing the boundary of your defined system, it is a transient energy. Its value and properties depend on the transfer process, and not just the state of the system. Now that we have clear understanding of this transient energy and its key characteristics, let's examine some common example of transient energy in action. Now, let's explore the two common and important types of transient energy that we encounter in thermodynamics, that are the heat transfer and work transfer. These are the primary mechanism by which energy moves across the boundaries. Heat transfer, often denoted by symbol Q, is the flow of thermal energy between system or between a system and its surrounding. This energy transfer is driven by a temperature difference. A fundamental principle of heat transfer is that the heat always flows spontaneously from a region of high temperature to a region of lower temperature. This is a consequence of the second law of thermodynamics, which we will discuss later. For example, consider placing a hot cup of coffee in a room. The coffee is initially at a higher temperature than the surrounding air. As a result, heat will transfer from the coffee to air, gradually cooling the coffee down until it reaches thermal equilibrium with the room. The energy crossing the system boundary is this heat transfer. Now, work transfer, often denoted by the symbol W, occurs when energy is transferred by applying a force over a distance. It represents the energy exchange with a system which interacts with its surrounding in a way that involves a force and a displacement. Work can be done on a system or by a system. When work is done on a system, the energy is being added to the system. When work is done by a system, energy is removed from the system. Consider a piston cylinder arrangement in an engine. When you push the piston inwards, you are applying the force over a distance. This work on the gas inside the cylinder. This compresses the gas, increasing its internal energy. The energy you supplied by pushing on the piston is the work transfer. It's crucial to remember that unlike stored energy, transient energy exists only during the process of energy transfer. It's the energy that is in motion, crossing the system boundary. Once the transfer stops, the energy that we has transferred becomes the part of the receiving system stored energy. Once the hot coffee reaches room temperature, there is no more heat transfer, and the energy that was transferred from the cup is now the part of the internal energy of room air and its surrounding. Now that we have a clear understanding of both stored energy and transient energy, let's bring everything together and define the total energy of a system. Now we have explored stored and transient energy. We can bring all the pieces together and define what is the total energy of a thermodynamic systems. The total energy of a thermodynamic system is simply the sum of all forms of energy that are present within that system at a given instant. It represents the complete energy content of the system, accounting for all contribution from various sources. Mathematically, the total energy of a system can be represented as internal energy plus kinetic energy and potential energy. It is important to note that this equation represents the stored component of the total energy. As we discussed earlier, the transient energy, that is heat and work, is energy that is in the process of crossing the system boundary. Therefore, transient energy is not included in system's total energy. Sorry. At a specific instant. However, the change, sorry, just remove this. However, the change in total energy of a system is directly influenced by transient interaction, that is heat and work. Think of it in this way: the total energy is a snapshot of the energy content within the systems at a particular moment. Heat and work are the process that cause the system energy to change over time. Thus, the concept of total energy provides a comprehensive accounting of the energy within a system, while recognizing that the energy can also enter and leave the system through these transient energy interactions. Total energy accounts for both stored energy and transient energy interactions in a system. It serves as a crucial foundation for applying the first law of thermodynamics, which we will explore in detail later. Now we have a clear definition of the total energy. Let's briefly discuss how it is used in various thermodynamic applications. Okay. Now all students know transient energy is not included in the system's total energy at a specific instance. However, the change in total energy of a system is directly influenced by transient interaction, that is heat and work. Now, we have defined the total energy. Let's discuss why it is such crucial concept in study and application of thermodynamics. Understanding total energy provides us with a powerful tool for analyzing energy transformation, simplifying thermodynamic calculations, and grasping the fundamental principles of energy conservation. Now, what is analyzation of this energy transformation? This is a key application of the concept of total energy in this analyzation of this energy transformation. Energy can change from one form to another. That is, kinetic energy becomes a potential energy, chemical energy can become a thermal energy, and so on. However, the total energy remains constant in an isolated system. This principle is formally stated in the first law of thermodynamics, which state that energy cannot be created or destroyed, only transfer or transform. Knowing the total energy allows you to quantify and track how energy is converted from one form to another. Just this is disturbing me. Now, simplifying the thermodynamic calculations. In many practical applications, kinetic and potential energy are often negligible compared to internal energy. This is particularly true in the systems where there is a little change in elevation or velocity. In such cases, we can often simplify our calculations by focusing primarily on the internal energy component of the total energy. These assumptions greatly simplify the energy analysis in a wide range of devices, including heat engines, refrigerators, air conditioners, and chemical reactors. Now, understanding this energy conservation is also important, as stated by the first law of thermodynamics, and which is a cornerstone of physics and engineering. It states that the energy cannot be created nor destroyed. It can be only transferred or transformed. This means that the total energy of an isolated system remains constant over time. Understanding total energy allows us to apply this principle rigorously to analyze thermodynamic systems and to ensure that our energy accounting is correct. To illustrate this, consider a steam power plant. In a steam power plant, chemical energy chemical energy from burning fuel is converted into thermal energy, which is then used to generate high pressure steam. The steam expands through a turbine, converting thermal energy into mechanical work. The turbine drives a generator, converting mechanical work into electrical energy. Throughout this entire process, energy is constantly being transformed from one form to another. However, according to the principle of energy conservation, the total energy of the system remains the same, validating that all previous explanation. By accounting for the changes in the internal energy, kinetic and potential energy, along with the heat and work transfer, we can ensure that the total energy is conserved. Now, we will move on to the next part, that is the summary of the today's session. Now, let's take a moment to recap the key concept we have covered today regarding the stored energy, transient energy, and the total energy. These concepts form a crucial foundation for understanding how energy behaves in thermodynamic systems. Stored energy is the energy contained within a system boundaries and is associated with the system's state. It is not only the process of being transferred The main forms of stored energy are internal energy, which is the energy at the molecular level, including the kinetic and potential energy of the molecules. Next is the kinetic energy due to the motion of the system as a whole. And finally, it is the potential energy, the energy due to system positions or configuration. The next important part was the transient energy. Transient energy is the energy that is in transition, crossing the system boundaries. It is not a property of the system itself. The main forms of transient energy are the heat transfer, which is due to the temperature difference. As we know, heat always flows from a hotter region to a cooler region. And next transient energy is the work transfer. The energy transfer due to force acting over a distance, work which is done on the system. And finally, we have seen what is the total energy of the system. The total energy is the sum of the all forms of stored energy within the systems. It is represented by capital E is equal to U plus KE plus PE. That is sum of internal energy, kinetic energy, and potential energy. Now, understanding the total energy along with the concept of stored and this transient energy is essential for analyzing the energy interactions in the thermodynamic systems and for applying the first law of thermodynamics. Now, by mastering this concept, you will be equipped with to analyze the energy flows and transformations in the thermodynamic systems. Applying the first law of thermodynamics to solve the practical engineering problems to design more efficient and effective energy systems. Understanding this concept is vital for anyone working with the energy systems, from designing efficient engines and power plants to developing innovative cooling devices. You have laid the groundwork for more advanced concepts. That concludes our discussion for today. Thank you for your attention and thoughtful questions. I am happy to address any remaining questions you may have. So please drop me a mail regarding this.